sketchy. Because I would like but some of these people are very sharp corners. You guys getting your walking shoes up for the march?
Good morning. Welcome. It's a little bit of a raining day, and it's my pleasure to introduce today's speaker, Kate Kiseeva from Oxford. And I guess you guys have been listening a couple of diamond inclusions and the mantle seamless talks in the last few months, and this is a continuation of this subject, and probably figured out that's something I'm interested in too. Anyway, so Kate actually did a PhD at Australian National Universities in 2012, and then went to University of Oxford for postdocs for 2 years, and then she actually received one of the prestigious what's a National Environmental
Natural Environmental Research
Council, yes, and NERC, and that's in the UK. It's a pretty prestigious grants and for her independently doing research at Oxford. And I crossed actually through my study and across several papers on majorite inclusions, and I was quite impressed with the work, and so I want to share that with everyone else and see what she has been doing. And by the way, and tomorrow she's going to give an informal seminar at 10 o'clock in boys' rooms on a totally different topic. And so if anyone interested, should come at 10 o'clock tomorrow. And Kate.
Thank you very much, Dave. When I was on the plane yesterday, landing in Dallas, I was thinking to myself, oh dear, I'm coming to this place where the experimental petrology has started, like the place where Bowen was working with Tuttle and Yoda, and it was absolutely amazing. It's only now that Craig told me that it was not actually in this building that, that Bowen was working, but nevertheless the place is just absolutely fascinating me, and thank you so much. I'm particularly honored to give a talk here, and thank you for inviting me.
Can you turn on your microphone?
I don't know how to do that. Now it's in my pocket. Is it on?
Oh, it's all right. It's probably.
She actually using the speakers.
Yes, now it should be good.
Is it better now?
Why is the microphone is not on?
The sound is probably turned off.
Yeah.
Okay, let's try like this. Better? Yeah.
Yes.
Better now, yeah? Oh, yeah, I can hear myself, great. So as Faye said a couple of years ago, I've got a grant that kind of entitled me to work on chalcophyll element partitioning between sulfides and silicates. A really fascinating topic, but nevertheless, for the last 7 or even more years, I've been working on deep carbon subduction, and this topic of majoritic inclusions in diamonds have never stopped puzzling me and have never stopped interesting me. So I decided now to slightly deviate from my normal work and to talk about this kind of a side project that I've been thinking about for the last few years. This work is done in collaboration with these people, and it wouldn't be able to publish anything or to do anything without them. So probably their input is actually bigger than mine. And I want to start saying that everything that relates to diamonds and to their genesis and to their occurrence is something, to me, very mysterious and very interesting. So everything is, I would say, different than any other environment on the Earth, I would say. And so I will start from a very brief introduction about diamonds in nature, their occurrences, types of mineral inclusions in diamonds and what they can tell us about the Earth's upper mantle, transition zone, lower mantle. Majoritic garnet, my favorite mineral, and the marker mineral for the mantle transition zone, and then what majority garnet can tell us about the transition zone compositions and the oxidation state. So as mentioned earlier, diamond, even as far as mines are concerned, something quite special. And this picture is just absolutely, to me, mind-blowing. This is the city Mirny in Yakutia, and these buildings are more than 9-story buildings in comparison with this huge mine pit, the Mir pipe. Mir in Russian means peace, so it's a very peaceful pipe, yet it's really big. It's more than 1.2 kilometers in diameter. And it's not the only pipe as big. There is another one, David mine in Canada, which extracts the purest diamonds in the world. And most of these diamond mines look exactly the same. So this is the profile of the Kimberlite Field. And you can see it looks like a long, huge carrot. The interesting thing, this is pretty much the only place from where you can recover diamonds. And diamonds in a kimberlite pipe can be recovered from different places, either from the actual kimberlite or matrix, or from one or the other xenolith brought by the kimberlite from the big depths, from about 100 to 150, even probably 200 kilometers. So diamond xenolith, or kimberlite xenolith, this is an eclogite that consists of two minerals, garnet and clinopyroxene. A lot of diamonds are coming from one of these types of rocks. This is a peridotitic xenolith that is olivine, orthopyroxene, clinopyroxene, and garnet. You can immediately spot the difference between the two types of garnets. This garnet is purple because it's more chromium rich. This is more red, more iron, magnesium, calcium rich. And also diamonds can, as I said earlier, found loose in the kimberlite matrix. So these pretty much are three types of locations where you get or extract the diamonds from, all coming from the kimberlite pipe. And this is my favorite slide, and I'm sure it's Steve's favorite slide too. So what I really like about this picture, and I think Steve made it really look well, that diamonds are actually coming not just from this area, which is the keel or the root of the lithospheric or craton, but they can come from anywhere in the upper mantle, anywhere in the transition zone, and some of the lower mantle. So even though the kimberlitic melts, or the onset of kimberlites, is basically linked to the craton and the cratonic lithosphere, the diamonds are from everywhere. And this is quite important because once you take the diamonds and look at the inclusions in them, you can actually find the inclusions from all these areas. And that's how we get the information about the, let's say, quite a restricted but still composition of the lower part of the upper mantle from the transition zone and the lower mantle. So now let's concentrate on the types of inclusions in diamonds. And this is probably the only way which can deliver to us material from such depth. The deepest drill hole in the earth is only 12.5 kilometers depth. So most of the data we get either from experimental studies or from seismics, but none of that is direct. And thus diamonds are probably the only potential tool that we can use, even though sometimes what they tell us doesn't always work out well and doesn't always tell us the correct answer or something which we expect. So lithospheric inclusions in diamonds are usually not deeper than 200, maybe at most 250 kilometers. So now we're looking at this upper part of this chart. And the chart I put it was done by Yurifuni and Ringwood. There were very similar charts by Fay and many other researchers. So pyrrolite, or peridotitic mantle, has olivine, a bit of garnet, and pyroxene. And then olivine changes the polymorph from alpha olivine to ringwoodite, wurtzlite. And pyroxene is gradually decreasing, entering the garnet structure, where the garnet from normal garnet becomes majorite. So in the eclogitic or mid-ocean rich compositions, we have similar thing but without olivine. It's clinopyroxene and garnet, a little bit of stishovite, and bigger pressures here would be coesite. So here again, clinopyroxene gradually decreases in the concentration becoming garnet. So in the transition zone we have, for the peridotitic rocks, garnet and olivine, and for the eclogitic pretty much garnetite with very little amount of silica. And now coming back to the lithospheric or upper mantle inclusions, again, everywhere will be defining as either peridotitic or eclogitic. And in E-type or eclogitic diamonds show as inclusions, usually garnet, clinopyroxene, and sulfides, which is minor phase. P-type or peridotitic, again, garnet, but you remember from the previous slide, it was slightly different in color, more chromium-rich, clinopyroxene, olivine, orthopyroxene, and again, sulfides. And this slide, even though from 2008 it could have changed slightly because more inclusions and more data was acquired, we can still see that there is predominantly peridotitic inclusions with about 30% eclogitic and websteritic are intermediate, or let's say pyroxenidic. So leptolite and Harzburgite are also, let's say in a broad sense, peridotite. Only leptolite is garnet with orthopyroxene and clinopyroxene. Harzburgite is just olivine and orthopyroxene. So one thing that already speaks for itself here is that the proportion of eclogitic inclusions is bigger than we expect the proportion of eclogite to be in the upper mantle. Because according to seismic studies, there is only about 5 to 10% eclogite in the upper mantle. However, the amount of eclogitic inclusions is much bigger than that. So there is a potential, I would say, disproportion of how many eclogitic inclusions are sampled by diamonds as opposed to how much eclogite is in the mantle. Okay, next, if we try to do more and to actually put this garnet and clinopyroxene into some kind of classification to see whether we can easily distinguish between whether the inclusion is peridotitic or the inclusion is eclogitic. Then this simple chart came from Sobolev in 1970s, and he just put it as calcium against chromium. Most of peridotitic inclusions would be very rich in chromium, while the eclogitic would be pretty much will have zero chromium. And that was a very, very good discriminator. You can see calcium all over the place, so very, very different concentrations for eclogite, very little calcium for peridotites, yet chromium is at much higher values in peridotitic inclusions. There is this again, this very, very kind of small field of websterite or pyroxenite, a hybrid rock between the two, which just a few samples over here, and they are a little more kind of offset from eclogites and coming towards the peridotitic side. But they're still not very rich in chromium, and they're mostly closer to eclogitic compositions. And again, garnet is different. This is more of eclogitic garnet, this is more of peridotitic purple garnet. So now we'll just jump from these upper mantle pressures all the way to all the rest of the mantle, down to the lower mantle. And if there are about 3,000 inclusions from this area, now we have less than 300 from all the rest, down to 800 kilometers. And this is quite fascinating that even this entire range of pressures discovered simply, but what we have at the moment is only less than 300 inclusions. And of course, this, as I mentioned, this is 2008, so there could be slightly more, but nevertheless, the proportion of what we gain from the deeper mantle is very, very little. And on top of that, probably because of the sampling issues and of the locations where these inclusions are coming from, the lower mantle quite shown by a larger number because of the Juína kimberlites in Brazil, where a lot of inclusions have recently been acquired from. So now we're pretty much left with the mantle transition zone having deep peridotitic, deep eclogitic, which is about 100 inclusions. So with lithospheric, and here being again the very big fraction, and lower mantle being about less than 8% of that. And as for the mantle lithosphere and upper mantle, we can again try to discriminate between the E-type and P-type. And here we get typical lower mantle assemblages like perovskite, calcium titanium, magnesium perovskite, or bridgmanite in perioditic ringwoodite was one single inclusion, woodsite, and majorite for both. And as I've mentioned, the majoritic garnet is stable throughout the transition zone in both lithologies. And sadly, this kind of a fairly interesting region of the Earth mantle, the transition zone, is only sampled by around 120 inclusions. So now I'm coming to the transition zone, something I want to talk about more, and what's so special about it. So the early studies by Birch in 1952 show that there is something unusual about this region, and unfortunately you can't see the axis, but the mantle transition zone is somewhere here, and the two discontinuities are not very well resolved at that time, but nevertheless he showed that there is something going on in that place. So then later Anderson and Zivonsky and I stole this picture from last week's lecture, where he showed very well the basically two discontinuities at 410 and 660, which are 14 and 24 GPa in pressure, and they are actually linked with the change in phase transition from olivine to ringwoodite and from garnet to majorite in this particular area. So on top of that, we do see these discontinuities in velocities, seismic signal, but on top of that, there's been quite a few studies, seismic studies, showing the transition zone is not different only through the transformation and phase composition, but it's also due to the some kind of like a burial place for the slabs, and some of the slabs, not all of them, get stuck in this area, probably bringing some heterogeneity or some different pattern or some kind of melting. So my goal was to actually study this area to see whether there is something special about it, maybe compositionally, or whether there is something special in terms of oxidation state that was somehow triggered by perhaps the stagnant slab, or perhaps by some kind of phase transformations happening in that area. So in this talk, I'll concentrate on two things. I'll try to use the inclusions, majoritic inclusions in diamonds, to infer of the composition of the transition zone and the oxidation state. So let's start from majoritic inclusions in diamond as a marker mineral and what we know about it. It's a simple garnet, but with a much higher silicon content in it. And because clinopyroxene is a silicon-rich phase, you dissolve the clinopyroxene component in the garnet with higher pressure, you basically introduce quite a bit of silicon, and that slightly changes the structure, although not by much. We also know that it occurs at the restricted range of pressures, and different papers quote different values, but the latest that I've heard was about 7 and 20 GPa would be the boundary for the majoritic garnet. Although I've seen the bigger range quoted too, it depends on the starting composition. So in eclogitic rocks, it comprises almost a monomineralic rock, while in perioditic it's coexisting with olivine. We only saw majoritic garnet as an inclusion in diamond, although there were quite a few papers that inferred to the presence of majorite in xenolith that was later broken down into normal garnet and clinopyroxene, and they're very rare. So this is one of the slides that was shown by Martin Wilding in his 1990 thesis that had never been published, and he showed this really lovely majoritic garnet that broke down into normal garnet and not sodium-rich clinopyroxene. And that's what probably happens with most of majoritic garnets which were delivered to the surface in mantle xenolith, and what at the moment we can never really see or kind of try to infer that their presence by doing the mass balance. So there are two types of majoritic garnets, and one of them, again, as we distinguish between perioditic and eclogitic, one of them is more common in perioditic rocks, another is more common in eclogitic. The point is the garnet has three sides: dodecahedral, octahedral, and tetrahedral. So tetrahedron doesn't really change. There might be a potential substitution of a little bit of titanium or phosphorus, but they are very minor. Then octahedral, we usually have in peridotitic majorite, silicon and magnesium substituted in an octahedral site, while in this particular substitution, the dodecahedral site remains untouched. So the name majorite comes from Alan Major, who was Ted Ringwood's technical officer when Alan worked in the Australian National. So this is pretty much like an orthopyroxene end member, and the important thing here is that you do enrich octahedral site with divalent cation, Mg, and silicon. So if we look at the second substitution, more common for eclogitic rocks, again the same structure of garnet. In this case, there is no divalent cation coming on the octahedral side, but instead we have sodium substituting the dodecahedral side, ending up with this kind of end member that was recently synthesized by Dimshitz et al., but that was first mentioned by Sobolev and Lavrentiev in 1971. So for this substitution, you actually deplete the structure with divalent cation. And just to summarize it, classical majorite for peridotitic rocks is magnesium-rich and silica-rich. For eclogitic, sodium-rich. This one will also have much more chromium, as we expect for the upper mantle garnets. The eclogitic high in calcium, higher magnesium numbers, again for the peridotitic rocks, and lower for the eclogitic. Number of the divalent cations increases with silicon, while on the eclogitic it will on the contrary be decreasing. So again, just judging by the proportions of rocks,